Hello, folks. Hopefully, you're enjoying this nice winter weather. I'm going to go ahead and continue on with our. This is going to be the start of chapter 4. We're going to look at the ozone that forms in the troposphere. We'll probably called smog, or how it relates to smog. Okay, let's go ahead and get started. We'll figure out what we're going to do in lab. We'll just have to push labs back and rearrange some stuff. But we'll get started eventually. So, tropospheric chemistry, especially smog. So, in the next couple chapters, we'll be looking at the chemistry of the troposphere. But this one specifically focuses on the chemistry that leads to the formation of smog. We're going to discuss smog, basically what it is, the different types of smog, and the conditions for its formation. There's a lot of complicated chemistry, usually involving hydroxyl radicals, the HO, and very volatile organic compounds, VOCs. But what is a volatile organic compound, real quick? Basically, organic compound is a compound largely of carbons and hydrogens, and occasionally oxygens, nitrogens. But volatile means it rapidly vaporizes. It goes from liquid phase to the gas phase very easily. Ether and ethanol, nail polish removers, these are VOCs, but so could be like benzene and other bigger compounds. So it's a catch-all term for a bunch of things. You hear about VOCs like off-gassing, and we'll talk more about those in later chapters, but off-gassing of VOCs, like buy new furniture, you gotta let it off-gas a bit before it stops stinking. That's the VOCs. So, exploring emission concerns of our vehicles. That's one of the things we'll look at later. Engine types, fuel types, and additives that we do, catalytic converters, and ways to control specific pollutants that help stop the chain that makes the smog. But smog has been ever present since even the 1600s. I love this quote, which is why I included it, but in 1661, John Evelyn described London as a cloud of sea coal, as if there be a resemblance of hell on earth. It is in this volcano in a foggy day, this pestilent smoke, which corrodes the iron and spoils all the movables, leaving soot on all things that it lights, and so fatally seizing on the lungs of the inhabitants that cough and consumption spare no man. Very evocative. But so what is smog? Smog is the generic term for air pollution that obscures the visibility by a haze of solid particulates or by liquid aerosols or a combination thereof. So, something's blocking the visibility. Aerosols in the air make it hazy. Now, not all aerosols are gonna be smog, but there are aerosols that make it hazy. Like, for example, if you ever go hiking and you look over a pine forest and you see it's very hazy over the pine forest, that's caused by the volatile organic carbon compounds given off by the pine trees, like alpha pinene. These producing liquid aerosols that distort the light. Originally, smog was a combination of smoke and fog. Now, there's two major types. One we will not focus on, which is classic or London smog. And instead, we'll focus largely on photochemical or LA type smog in Los Angeles. Now, classical smog was mainly from coal. We don't use coals much, so it's not as big of a problem. But back then, coal was ubiquitous form of heating and light and all that. So high concentrations of unburned hydrocarbons. So some of that fly ash and whatnot from the coal that didn't burn up, given off. Anyone who's ever been to a blacksmith forge, when you first put the coal on the fire and it starts to burn, it's producing large amounts of smoke, black and greenish and grayish smoke. As it eventually starts to burn hot enough and burns off some of these VOCs, it'll be a cleaner burning coal, but initially it's very smoky. Elevated levels of atmospheric sulfur dioxide is some of it. It can produce some of the greenish color. It's mildly reducing and acidic in nature. So it means it reduces, it's non-oxidizing, it's reducing. And acidic means it can form acid rain and dissolve certain things. So in high humidity, it forms a very irritating fog by binding to the water droplets. We'll talk more about this in acid rain chapter. But in London and other urban European cities that used very high sulfur coal, it gets released near the ground level with no pollution controls, and so it was a major problem. Now, of course, they wouldn't want to choose high sulfur coal if they had other opportunities, but the coal in that region was usually high sulfur, so you can't really help. You use what you have. In 1952, a severe smog lasting weeks led to the deaths of over 4,000 people. So basically, the weak and already unhealthy, it finished them off. But you can't just like, smog out, stay home. It's like you had to go and work, and so when you're already in a weak constitution, it's damaging the lungs, and it helps lead to diseases of the lungs and consumption and whatnot that kills you. Now, it's still a problem in Eastern Europe, which is largely coal-based, in China and India. It might be less of a problem in China, but there was times when we had, like, for example, the I think Olympic Games quite a few years back, and it was like we were worried about would our athletes be able to breathe because of these. You had like smog warnings, like do not go out under these conditions. But fortunately, rain washes away most of this, and so there was a big rain before the Olympic Games, and it managed to clear up the air quite a bit. Now, photochemical smog is where we're going to really focus this chapter. Now, this is largely coming from petroleum combustion, principally from motor vehicles. But it's a very complicated sequence of chemical and photochemical reactions that happen under very specific conditions that produce photochemical smog, which is why places like Mackenzie isn't really suffering from a lot of photochemical smog. But places like LA will. But it contains very elevated oxidants and carbon-containing reaction products. But this is more of a 20th and 21st century problem. But it needs quite a few things. It needs unburned hydrocarbons, it needs some NOx, some NOx, and which the NOx is produced by the internal combustion engine in our vehicles. We need very specific weather conditions. We need high temperatures, very intense sunlight, and we need a very, very stable atmosphere, which occurs during a temperature inversion. We might talk about this a little bit later, but the idea is like, remember, hot air rises, cold air sinks, and if the air temperature is right, you'll have a place where it'll basically lock in the conditions of the air, and so we don't get mixing. But this is often found in Los Angeles, but it's now widespread in North America and Western Europe. It can occur in Mexico City, Cairo, Lagos, Jakarta, Johannesburg, Beijing in 2008. But It can come from a wide variety of fuel sources: kerosene, charcoal, and a wide range of biomass sources, because all these fires can produce NOx gas. But the presence of dust and other particulate matters can aid the production of photochemical smog. But we'll see. It's a complicated process. This image on the top right, A, shows the idealized photochemical smog event. Down there in B shows actual data from Toronto, Canada on May 21st, 1992. That as the day progresses, it shows NO builds up and it starts to decrease as it's converted into NO2, and it starts to decrease by around noon. Hydrocarbons builds up by 8. Of course, you can see they're building up. They're building up. Why are they building up? Well, because rush hour. It's not really a lot of people driving around at 4 in the morning, but by like 7 or 8, you get a large amount of vehicles. Then as the day progresses, hydrocarbons are converted into aldehydes, and the NO2 and NO are converted into the other oxidants, and they build up, and then near the end of the day, everything drops back off and goes back to the original starting regions. So 6 a.m., traffic picks up. You increase the VOCs and NO. NO should increase and then decreases as it converts into NO2. So, yeah, as I said, at midday, yeah. So, as you can see there in the actual situation, it's not quite as clear. The NO2 doesn't jump nearly as high as it shows, as is predicted. We see various wobbly amounts of ozone, bad ozone, being formed as it peaks up and drops off a little bit, and then peaks up and then drops off, and peaks up and eventually drops off at the end of the day. So we see it's not quite as idealized as we see in the above chart, but it's pretty good. So these partially oxidized hydrocarbons are what, when we go to aldehydes and whatnot, are what it's going to cause the haze. The ozone acts as an ecotoxicological problem. The aldehydes aren't as bad for us breathing. It's still not great, but the ozone is what's the more dangerous. So, the one of the key features is we need to form hydroxyl radical. So, it starts. The formation process is centered around the formation of hydroxyl radical, but the first thing we need is to form our NO. So N2 plus O2 in a combustion engine, we talked about this chapter 1. It converts to 2 molecules of NO. Now, in the air, once it's pumped out of the tailpipe, it doesn't really convert back. So, but it's a slow process where NO and O2 can form NO2. This first step is rather slow. But unfortunately, as things get going, there's other ways to form NO2, such as ozone. So initially, it's a slow build. But once we get some of the other byproducts, we can keep this cycle going in other methods. But the likelihood of 2 NOs bumping into O2 it's not very reactive. So while the NO plus ozone is rapid, ozone is a byproduct that gets formed later, so this reaction cannot occur until we get a big buildup of NO2. But a third route involves peroxy radicals. So peroxy radicals can donate an oxygen to form a hydroxy radical. The R just stands for generic hydrocarbon, like unburned, partially oxidized hydrocarbon. That we're not specifying its chain length or what is attached, just it's a bunch of carbons with a peroxy group. So this can be a byproduct of vehicular emissions. But so this NO2, once we start to build up this NO2, this NO2 can absorb both visible and ultraviolet light, wavelengths of less than 400 nanometers. This NO2 will split into NO, back into our NO and into monooxygen. Now in the troposphere, this monooxygen, if it bumps into oxygen and nitrogen, which oxygen is pretty concentrated, nitrogen is also pretty concentrated, we form ozone. As we know, ozone can photolize from intense sunlight back into excited O2 and excited monooxygen. Now, the majority of this excited monooxygen will be deactivated via collisions with other dioxygens or collisions with dinitrogen. But if the humidity is right, and so we get enough water, the excited oxygen will bump into a water molecule and strip off a hydrogen to make two hydroxy radicals. So what we're saying is that monooxygen alone will not strip off the hydrogen, but the excited oxygen will. So that monooxygen will bounce around, not doing a lot of reactions until it bumps into an oxygen and forms ozone. And so we get this ozone decomposition reaction continuing until the excited oxygen bumps into a water. But so the net sum of this three-step process is that an NO2 and a water molecule go back to an NO and two hydroxyl molecules. Given enough time, that's what's occurring. Now, another mechanism for hydroxyl radical formation is especially important in heavily polluted areas. So ones where we have a lot of NO and NO2 buildup. So NO bumps into NO2 and bumps into water, forms two molecules of nitrous acid. Two molecules of nitrous acid. These molecules of nitrous acid can be excited with light and go back to NO and OH radicals. So we don't have to wait for the excited monooxygen to run into water. We can form this nitrous acid and then let that be excited. And the still net effect is NO2 plus water forms two hydroxy radicals and an NO. So the idea is for every one NO2 you have, you're forming two hydroxyl radicals. So for every one NO2, we're forming two hydroxyl radicals. Now, hydroxyl radical concentration depends on conditions, but it could be from 2.5 times 10 to the 6th molecules, so that's 2.5 million molecules per centimeter cube in urban, to 100,000 in rural conditions. So it's not absent from rural, it's just lower concentrations. This tends to be higher in tropical environments where you have higher temperature and intense sunlight. More sunlight, more splitting of ozone, so the more likely we're going to have these photochemical reactions occurring. The high intensity light that we need to split these molecules up. So, besides nitrogen oxides, internal combustion engines release a lot of unburned volatile hydrocarbons that can be oxidized through reactions with hydroxy radicals. So rather than give a formula, we're going to use a generic aliphatic hydrocarbon, RCH3. Aliphatic just means single bonded. It means it's all single bonds, no double bonds. It's a hydrocarbon chain containing only single bonds, so only carbons and hydrogens. we get a wide variety of things that are coming off the octane when it doesn't get fully burned up. So we're just saying the main thing is that we need the presence of a CH bond. So rather than try to define 15 different reactions, we're just saying some sort of hydrocarbon with a CH bond. So this hydroxy radical steals a hydrogen off a CH bond. Now this CH bond is now radicalized. It can bump into the oxygen that is present in the air, which there is a lot of, and it forms a peroxide. It needs something to help shake off some of the energy, but there's plenty of atoms in the air to do that. Now this peroxide can now help produce NO2 from NO, which is now produced by the pollution. And it forms an alkoxy. So instead of a peroxy, it's a kind of like an OH, except it's now a CO radical. Now this CO radical can bump into another oxygen, which there's plenty, and it steals another hydrogen, and it's fully oxidized to an aldehyde. The CHO, the CHO aldehyde, is a terminal carbon oxygen double bond where there's a single carbon hydrogen bond that caps it off. But the aldehyde functionality is a C double bond O. And the H is bound to the carbon. And so we form a peroxy radical. And that peroxy radical can then reform an NO2 and an OH radical. So you can see right here, so we formed we start with a hydroxy radical. And part of this process, we form two NO2s from NO, and we reform our initial hydroxy radical. So hydroxy radical is acting as a catalyst with these unburned hydrocarbons, and it produces two NO2s to run through this cycle. So it is you can see where this can easily spiral out of control once it gets started. Once we get through the initial slow steps of forming the hydroxy radical by getting NO2s. So if we incorporate this into the earlier cycles, the idea is like for every one unburned hydrocarbon, you're getting one aldehyde and 4 hydroxy radicals. So, oof. So we're quickly building up a crap load of hydroxy radicals. So this can quickly spiral out of control. In general, the hydroxyl radical plays the catalytic role. So we only need very small amounts to produce a lot of byproducts. Now, if there was no competing mechanisms to remove hydroxyl radicals, this oxidation of alkanes would only continue to accelerate. However, if we have enough NO2, hydroxyl radical plus NO2 forms nitric acid rain. That removes a hydroxyl radical and an NO2. Two of those peroxy radicals that were byproducts of the oxidation forms hydrogen peroxide and oxygen, which can come out in the rain. Very oxidizing condition. And a peroxy radical and a hydroxyl radical can also convert back into water and oxygen. So these products of these reactions are relatively stable, and most of these can be removed through rain. Not saying it's great, but it helps reduce and normalize our atmospheric conditions. The hydroxyl radical also requires sunlight because it's a photochemical process. So this is also why this resets at night. You can be producing these hydrocarbons because people are still on the road, but all these hydroxyl radicals that are in the air will stop being produced because the NO2 is no longer split up. The NO2 no longer gets split up by the light. There's no longer any light. So the NO2, as it builds up, reacts with these hydroxyl radicals that are present and gets converted into these other byproducts. And so it kind of, that's why we reduce it back to near starting conditions. Now, there are some secondary reactions that can also occur. These aldehydes that are being formed through the oxidation of hydrocarbons, two other major byproducts can be formed. First is ozone, which can form through the photochemical splitting of nitrogen dioxide and with oxygen to form ozone. The first major, when we do the smog, is ozone, but we also produce something called peroxyacetic nitric anhydride, abbreviated as PAN. This is the byproduct of the hydrocarbons. So, PAN is a major eye irritant. It's oxidative, it's acidic, and highly reactive. It's a major eye irritant and a reservoir for NO2, and storing it and allowing this to be transported to somewhere else. Much in the same way when we talked about the ozone layer, that these NO and NO2 can be trapped in these holding cycles and then allowed to be blown by the wind or transported to like the Arctic Circle. So the aldehyde, once we get the aldehyde, it can react with hydroxyl and it pulls off a hydrogen. So we have an aldehydic radical. This aldehydic radical binds to oxygen to form a peroxy anhydride. And then this peroxy anhydride, or this peroxy acid, binds with NO2 to form the PAN. So looking at that, we have a C, double bond O. And then to that same original C, we have a single bond O. That O is single bonded to the second O, and that O is single bonded to the N, which is then bound with the NO2, which is bound with the two oxygens. So that is PAN. It's trapping that, and it can break back apart. So the nature of photochemical smog. Due to this complex series of thermal and photochemical reactions, a number of chemicals would be elevated. NOx, VOCs, aldehydes, oxidants, ozone, and PAN. But some are gases, but some of them, like the aldehydes, will actually form small liquid droplets as aerosols, and they cause the hazy appearance in the smog. Now, if you get a yellowish haze, that is due to the color of the nitrogen dioxide. But so we can see a kind of a complicated series of reactions right here on the right. The N2 plus O2 forms the NO. Various processes you can form NO2. The NO2 can go into nitric acid, but it can also go into forming ozone. Ozone forms hydroxy radicals. Hydroxy radicals reacts with the unburned hydrocarbons through the various processes, producing more NO2. And this can go to the aldehyde. But this cycles around to the peroxy, which can form more NO2, which can either go to acid rain or keep on cycling around. You can see it keeps on building and building. So in polluted areas, the concentrations can be between 10,000 ppBV to 30,000. Unpolluted, it's less than 200. Nitric oxide, 100 to 400 versus less than 20. Hydrocarbons, 600 to 3,000 versus less than 300. Ozone, 50 to 150, less than 5. Pans, 50 to 250, less than 5. So let's see how we're doing on time. So that's 30 minutes. I'm going to go maybe a little bit. I'm going to go further. Now, looking at oxidation of other volatile organic compounds. So in our reaction mechanism, we used a generic hydrocarbon, but there are actually a wide variety of VOCs. These can remain unreacted in our atmosphere or can be oxidized by hydroxyl radicals, as we can see. In fact, alkenes, which are unsaturated double-bonded hydrocarbons, react faster than alkanes, our saturated aliphatic ones. And even in the unreacted states, many of these hydrocarbons can be irritants or even carcinogens. There are two mechanisms by which a hydroxyl radical initiates an oxidation, one of which we already covered. The first mechanism, the type of carbon can actually change the reaction rate. Here's an example of a bunch of different hydrocarbons. You can look up what they look like, but toluene, MP, meta or paraxylene. Toluene is a six-membered double-bonded ring. It's a benzene with a methyl group. Meta, paraxylene, and orthoxylene, they have a benzene with two methyl groups, either in the 1,2 position or 1,3 or 1,4. Benzene, ethylbenzene, trimethylbenzene, ethyl-4-methylbenzene, hexane, six-membered ring, heptane, and 1-ethyl, 2-methylbenzene. So those are just largely rings with substitution. But so, reaction pattern, primary position, or the terminal position, is the slowest to react. Secondary reacts faster, and tertiary reacts the fastest. Quaternary, where there's no CHs, does not react at all by these radical mechanisms. But the hydroxyl radical can also react with unsaturated hydrocarbons, where it can add across a double bond to create a new radical, but we have this hydroxyl group on there. So after the initial addition of a proxy radical can form with oxygen. And then this can react with NO to form the alkoxy radical, the same way we did. Except now we can see a cleavage of the carbon-carbon bond to form an aldehyde and a new radical. And so we end up forming two aldehydes. And we regenerate a peroxy radical. This is kind of similar to a reaction that people learn about in organic chemistry, where we use ozone to split and oxidize a double bond. It's kind of similar to that, except a little bit less complicated of a mechanism. But the idea is we still form a hydroperoxide, and we're still forming an NO2. In this case, we're forming two aldehydes. Now, an alkyne, a triple bond, can undergo a similar reaction to form a dialdehyde and a formic acid. So formic acid is a simple carbon double bond oxygen and then OH. Acetic acid, vinegar, is a type of acid in the same way, but formic acid is a one-carbon version of that. Well, aromatic compounds, which is our benzene rings and our toluene and our xylenes, if there is an alkyl substituted to the ring, if there's a carbon substituted to the ring, it always goes through the first mechanism. But if there is no hydrocarbons bound to the ring, you can add the peroxide on the radical onto the ring, and it gets substituted thusly. And these phenol and peroxy radicals can fragment to form we form a phenol and a hydroperoxy. So multiple fused rings, like called polyaromatic hydrocarbons, are very stable to oxidation. So they have long atmospheric lifetimes. So we can get some of these guys that will hang around and with plenty of time to react. But so nearly final products of photochemical oxidation. So aldehydes and ketones, which are similar to aldehydes, are important products of several oxidation schemes, but these guys can go on to react. So I want you to think back real quick on how aldehydes reacted with the hydroxy radical, and then followed by a dioxygen addition to acetyl peroxy radicals. So, well, this acetyl peroxy radical can help form NO2, and we can also cleave off some of these guys to form a methyl radical in CO2. So cleave off the carbon OO to form CO2 and methyl radical, which the methyl radical will form an NO2 to restart the cycles. Before it can form more hydroxyl radicals and more aldehydes. So alternatively, these aldehydes in the atmosphere, if they have very high intensity light, around 290, we can cleave these aldehydes into their own radicals, either being methane and carbon monoxide, or methyl radical and the CHO radical. So the final products of these aldehydes, they either end up as PAN, some sort of alkyl radical in CO2, or some sort of alkane in carbon monoxide. So the lifetime of the average aldehyde in the atmosphere is about 24 hours before it gets converted into one of these byproducts. So they don't hang around that long, so they keep on resetting. We will go ahead and stop there. We will not talk about methane at this time, but we will pick up from here when we get back.